Hello everybody. Welcome to, I guess it's the second to the last week of, or almost the last week of MI205. Just a few bookkeeping issues to wrap up. Remember, we have the final became live today, so you can actually take a look at the questions and begin to answer those from the training site. That'll close next Thursday. And the project is due next Friday. And people ask, how long will the site stay up, or how long will you have access to it? Through the end of the year. I think that's as far as that we're going to guarantee. It may be straggling up after that, but I think through the end of this year, through December 31st, is when you'll have actually access to the site, for sure, absolutely. And then after that, you may or may not. It depends upon how quickly we remove users and get it cleaned up and ready for the next class. Again, as always, ask any questions. Today what we're going to do is we're going to continue on with the lecture. We have just two short topics to cover, and then we'll jump right into the homework. I'm also free to answer any questions that are general about the project, if there are any. I know some of you have been posting onto the website. That's been very helpful, I think, for others who might look at those answers and if they had any questions. So let's jump right in today. We covered last week a little bit of how to run NONMEM, or how you might do it with MetRG. We talked a little bit about plotting with NONMEM. Now we're gonna look at a different type of plotting, and so a different output. And so in this case, what we're going to cover today is a little bit of reading and plotting WinBUGS output. Now, what I'm not going to do here today is really walk through the code and kind of explain everything that's going on, because there's a nice, fairly large chunk of code, and there's lots of things happening in that code. I think what our goal here really is to make those of you aware, obviously, and most of you are probably, that there's the application of Bayesian analysis in this field of pharmacometrics is growing, and it's being used as a tool. It really helps. It's mostly been applied, as we can see it, in early development. So early decision making, maybe go/no decisions in phase 1 or phase 2, or helping make some decisions like that. Not so much in late stage. So what we're going to really limit our application to today is reading in a previously saved output, and how you run it and everything. We're not going to be able to get into that today. However, we're going to read in some output that's already been run, and then just generate some plots to show you what they might look like. And you, of course, will have the code available to you, so that you can do some plotting on your own. And so the model that we're going to be talking about is listed in item 8.1 here. It's a simple linear regression model, slope-intercept model with some residual error term. And we're going to use the R feature called load that basically will load a file that was saved with the R feature called save. And we're going to use a set of functions called bugstools.r. And those functions are freely available from Google Code, and we've listed where you can get that information. And so let me just quickly go ahead and load that piece, and we could load it something like the following, depending upon what the object name is. In this case, the object was called linear1b.fit.rsave, so we're just going to go ahead and load that, and we can say do a str on bugsfit, because that's the name of the object. And we can see there's quite a few things here going on. It's basically a list of 24 items. Everything from the number of chains you might have run, iterations, lots and lots of different, it basically captured information from the output of a WinBUGS run. And now what we're going to do is we're going to go ahead and I've already supplied to everybody in your zip file that you received, there's a linear directory, and in that directory is the information, is this model directory called linear1b, and inside of that there's a linear.txt, which is we've seen this before. This is the model file for that model we just talked about. So what I'm going to do is just go ahead and set a few objects, or I should say set a few variables here: course directory, model name, example directory. And we're also going to then set the working directory to course year, and we're going to load a couple of files. In fact, this we've supplied this to you, this bugstool.r. I'm not going to spend a lot of time on it, but suffice to say, this is just a bunch of different R functions, a number of R functions that are helpful for plotting outputs of MCMC analysis in WinBUGS. Okay. So now we've sourced that. Now we're just going to go ahead and generate a few. Again, we're not going to, this is just generating some information for the actual WinBUGS run. So things like what the data is, because it's the functions that we're going to use to do this plotting and generate some tables take as input things like bugs.data, parameters to plot. These are just simply parameters of the model. You can think of them as things just like clearance and volume, something like that. And then we're going to do, let's enter those. And then we're going to do just some reformatting. So this is simply going to pull out one of the bugs fits objects, and then it's going to do some basically rearranging of that object to create an object called posterior. And now we can get to the meat of the problem. So now what we're going to do is we're going to do some plotting. So this is something that you've probably all seen before. You might have even generated it for your current project. This is just basically opening up a PDF device and saving it to a given name. There's just a lot of variables being used here to generate the name. So course directory, example directory, model name, and then the plots.pdf, and then just some arguments for the width and the height of the PDF. So what we're going to do is, to make it relatively simple, we're going to go ahead and just source all of this. And all of this ends in the dev auth because we've opened the PDF file, so we have to close the PDF file. And so now if we want to go and take a look at what it generated, we can look in the linear 1B directory. And now what we're going to see, you may or may not see this now, but we know that this is a new one because the date on this particular plot is 12/9 and 12/9 for this CSV file and this plot file. So first we can look at the CSV file. Just simply a table of results. Probably easier to read it in something like Excel. This is just basically giving you the parameter name, the mean value, the standard deviation, time series, and then actually the percentiles of that along with an effective n. Again, we're not going to cover here what they are. Just suffice to say that assuming that you've gotten that far, you can use this script then to summarize some work you've done. It also generated some PDFs, and these are what's called trace plots, or history plots really, of the different parameters as you move on through the samples. Sometimes these are referred to as fuzzy caterpillar plots. The idea being here that you want to have a nice kind of oscillation here about some central value. You don't want to see a lot of peaks and valleys and things like that. These are then the distribution of those actual samples, and then these are some Gelman-Rubin statistics plots to kind of tell you whether or not you've reached a quote-unquote convergence with your model. And then finally, here's something. This is just observed, predicted, and then confidence, credible intervals around that. So again, just a simple linear regression model. So we have a predicted line, and these are observed, and these are the credible intervals around those around that predicted line. So again, I think the point here wasn't so much for this particular example, wasn't so much to give you a lot of background on, say, WinBUGS or Bayesian analyses. We have a whole course on that kind of walks you through that, but really just to demonstrate the fact that, with a little bit of effort on your part, maybe in using the tools we've developed, R is a nice back end to WinBUGS, because again, there's some graphical pieces built in there, but as usual, R is a nice place to do some of the plotting because then you have a script saved and it's kind of easier to reproduce it in the long run. And we've given you all that code that you can take a look at and kind of work through, assuming that you have that you've done this kind of analyses. Okay, so the last topic really we have in this week 8 is summarizing non-mem runs. So as you can imagine, when you do non-mem analyses, when you do population PK or PK/PD analyses, you run quite a bit of models. We've really only run so far in this class just model 1 and model 4, and they're just different. They're just different examples of the plots that you can generate with non-R. But you could envision if you were doing this for say a pop PK analysis for submission, you might run 10, 15, 20, 30 models, and one of the things you need to generate is a run log for those models. So built into MetrumRG is a function called rlog, and we can take a look at the arguments for rlog. First, it'd be helpful if I loaded the MetrumRG package. So let's do that. So I've loaded MetrumRG. Just make the screen a little bit bigger so we can see things here. And we can take a look at some of the arguments. Actually, these arguments are similar to the ones that we saw that we're seeing for the other MetrumRG packages for running NONMEM 7.2. For example, we have a run number here. This can take a single run number like 1, or it can take a vector of run numbers like something like that, 3 to 10. So it'll go through and do this for each of these numbers. Project is simply a project directory. The majority of these other ones you can let in the defaults they have. The main difference here is this tool variable here, which refers to what version of NONMEM you use to do the analysis. And in our case, we've actually used NONMEM 7, and that's all you really are exposed to on the Metrum RStudio server. So we're going to substitute their tool for NM7, and a very minimal, relatively minimalist call for rlog is what you see up here on the screen. This window a little bit bigger here. So basically, it's very simple. We have pass it a project, which is home Bill K, MI205, modeling out of R. The runs that we want to specify are 1 and 4. The tool that we used to analyze these runs was NONMEM 7. And append equals false. One of the things that happens when you run the rlog function is it generates a run log file. It's a comma delimited file, and we'll take a look at it in just a second. Append equals false just says, do I want to actually create a new file when I run this, or do I want to append the one that's existing? Most of the time we append equals false because this function takes very little time to run, so you can run it many, many times to generate a new run log every time that you run a model. So let's take a quick, we'll go ahead and run this. And we didn't get any errors, which is good. Now, and before we get to the output, let's say that I put a number in here that we didn't have a model for, like we don't have a model 5. What would actually happen? Well, nicely enough, the function still completes. It just passes on an error message for that one particular control stream. And so one of the things it looks for is a file called 5.ext from a NONMEM 7 output. And so it didn't find that. So it went about its merry way and processed the others, but it said, I didn't find 5.ext, and that's just a message so you're aware. So if we go over here to the files window, I'm just going to go ahead and refresh that so that what we'll notice is we now have a log called com_runlog.csv. Let me just make that a little bit bigger. Not so helpful to look at it inside of a text-based. It is a text file, but it's probably better to look at this in something like maybe Microsoft Excel, or even reading up and looking at it in R. In this case, what we have is we have a comma delimited file that lists, in the first row it lists, let's see if I have a copy of this on my local machine that I can actually open up in Excel for you so you can see. But basically it lists all the non-mem output. Just bear with me a moment here and I'll get this open and then we can take a look at it in Excel so we can actually see this a little bit better. Okay. Okay, so Excel's opening up here. Okay, so now what we see here is that same file, I just opened up in something that's a little bit easier to read. And so basically as you move across from left to right, what you see in these different cells in A and B is simply what's listed in your problem statement. So it captures verbatim what's in that $ problem record of your control stream. This is just whether or not you've minimized successfully in covariance. This is your objective function value from non-mem, and then across from left to right are the parameter estimates. So depending upon what they were specified in the model, they will correspond to clearance or volume or Ka, whatever the particular parameters are. And then at the very end, it lists you the run number we're talking about. So in this case, it was run number 1, and then it lists you the actual control stream that was used in the run. Now, as you'll notice in run 4 here, we have a different control stream, different control stream run number, different data set, and so we have a different, these parameter estimates don't necessarily line up one-to-one, say model 1 to model 4. It's really up to the user to kind of define or to know what corresponds to what. There's other methodologies that we have built into MetrumRG. If you decide to use that package, it'll kind of generate some other tables that you can use if you want to associate parameter estimates with a given parameter name. But in this case, you kind of have to rely upon yourself to pop open the control stream and know that as you move from left to right, it's the thetas, the omegas, and then the sigmas, the outputs that are listed here. So I got a question here. Let's take a look at what that is. So somebody wants, actually, it's a good point. So somebody wants to know what's the benefit or what's the advantage of, here at Metrum, we use the MetrumRG package for doing non-mem analysis. So, a set of R scripts basically versus using some of the GUIs. Some of the GUIs that are out there are things like PDX-Pop, it comes to mind. I can give you our slanted bend to some degree. As I was involved with PDX-Pop early on, when it was in its infancy, really, and I can't speak to exactly the version that's out there now, but I think what we've found is that very quickly when you're moving along in the field of population analysis and pharmacometrics, some kind of a GUI to run non-mem has limitations. What I mean by that is you still, most of the time, you have to write a control stream. Sometimes you have limitations on the plotting that can be done. Eventually, what you're going to have to do is open up R and dig into the output file and generate some plots. And you're going to need R to do things like formatting data. So our approach really is have one tool, R, with a set of packages and functions basically that allows you to stay in one environment. So it allows you to stay within R to do things, everything from merging, dosing and concentration and covariate data and efficacy data into a file, running non-mem, doing some general plotting, and then doing some additional plotting. Because I think very quickly you'll realize that no matter what tool you use, the standard set of diagnostic plots that are generated, they're fine from a day-to-day basis for looking at models, but more often than not, you're going to have to generate some plots on your own, generate some post-run plots on your own. And if you're in an environment like R, then you have access to all the tools in R, and you work from one single script. That keeps track of all the runs you've done. It's really a matter of what we've gotten used to using here and what we kind of support. And also the fact is then with with our MetroMRG package, you know, there's the whole NM-qual, the NONMEM installer. So I don't know that there's not necessarily, I'm not going to argue for or against using a GUI like PDX-POP or some of the others, but I guess I would just say that sometimes very quickly you outgrow that point and click interface when you start to get to do more complex modeling, and you have to generate control streams anyway, and so using R and doing everything from R is kind of a one-stop shop. Okay, so enough about my soapbox for using MetroMRG. So that kind of completes the lecture portion of this chapter, and so that combined run log that I showed you, that CSV file, can really make the basis for, say, a model building summary table that's always part of a PK or a PK/PD analysis. There's usually a sub table that's part of the main text, you know, or main table set, you know, maybe of you know, the 10 or 15 key models, and then that combined log.csv file can be submitted, say, in an electronic submission, is to be kind of a record of all the runs that were done for a given analysis. Okay, so that finishes up the lecture for today. So what we're going to do now is we're going to move into the homework. So we'll go ahead and jump right into that. I've already done the library MetroMRG, so let's take a look at the first homework problem that we talked about doing. So what I asked you to do was in the MetaSub example that we had done from class, we generated 10 new control streams from one control stream. What I ask is, how could you change this code to generate 100 or even 200 control streams? And then what if for some bizarre reason you wanted to generate control streams that started from 200 or 300, or really what you wanted to generate a control stream that was incremented every 2. So instead of going 200 to 300, you might go 200, 202, 204, 206. Other than to do that, because I ask, I can't think of any other rational reason to do that. But nonetheless, let's say that we wanted to generate control streams with the names 200 to 300, or 100 control streams. The MetaSub call that I have up on the screen was something we could use. So we're going to read in that same 1.ctl file. The only argument that you have to change really is the names argument. That represents in MetaSub the portion that's going to generate going to be used as the names for the new control streams. So this MetaSub call, as it looks here, should generate control streams 200 to 300 from 1.ctl, and they're going to put it in my MI205 modeling out.r. And for those, everybody should remember now, or probably is used to seeing tilde just as represents your home directory. So if I do MetaSub and I submit that, and I come back over here to the window, and let me just do a refresh on that. So what we see now is we see control streams 200 to 300, and we can take a look at one of those if we wanted to, and we can see what I'm asking. What I wanted it to do was I wanted it to take the wherever it sees x1 r.csv and replace it with the name as numeric, and the name is going to be the internal numbers, so 200, 300, 200, 201, 202 with the .csv ending, and then also wherever it sees $table, replace it with semicolon $table. So if we look at 200.ctl, we'll see that the 200.csv was substituted in the right place, and we have semicolons for all the table places. And if we're just gonna, let's just pull up randomly another one. If I were to pull 210 up, what we see is 210.csv, and we see the same substitution there. So again, this is just a way of using MetaSub to generate 100 different control streams. So the next one here, the second part of this was, what if I wanted to generate these, the same thing, except now generate them every 2, so even numbers. every 2. Well, the key here is no real changes to, the only thing we have to change is the sequence, and I chose to do it from 3 to 400 because if I did it from 200, I would just be overwriting the ones I already wrote, and I wanted to demonstrate this. So now all I did was, instead of passing in a vector of numbers, I just passed in a function to the names argument, and what that function is going to do is generate names every 2. So it's going to generate a sequence of numbers that go from 300 to 400 by 2. So if you're down here on the lower box, we have 300, 302, 304. So it's only going to generate the even numbers here. The rest of the call is exactly the same. So if I go ahead and submit that, and we look over here to the right, now what we see here is we see same thing, 300, 302, 304, 306. And if we click on one of them, we'll see that 304 has 304.csv as the name of the data record. And it has semicolons in front of each of the tables. So it's going to comment those out. So again, not rocket science, but just an interesting way to be able to do a sequence of numbers. So let's see, I have another question here. Let's take a look here. Somebody asked, can you use the MetaSub argument to generate data for simulation? Well, the MetaSub argument itself takes a pattern and a replacement. So if you had some kind of a data set that was ASCII text and you could search for some pattern, maybe you wanted to replace all the amounts that were, say, 500 and replace it and change it to amounts that were 1,000, you could do something like that. But you wouldn't be able to, I don't think at least, you wouldn't be able to use MetaSub to generate a skeleton data file. You kind of got to do that on your own. I mean, that takes a little bit of effort. That is the only probably downside of not really downside, but one of the things that needs to be done when you do simulation with NONMEM. You need to specify or create a skeleton data set. Being the MetaSub has to start with something. I think that the effort you would go through to generate a skeleton file with MetaSub or starting with the data set, you might be able to start with the data set and blank out all the concentrations, but that really wouldn't help you anyway because that would be done automatically by NONMEM when you did the simulation. You're better off just writing a data set writing a set of an R script, and you can do it actually relatively easily. I would point you in the direction of a function called expand grid that takes a couple of arguments that will, that'll take something like a set of times and a couple of other factors and do a kind of a factorial spread of that. So for every ID and every, say, male and female and every weight, it'll generate a new set of times. So it takes minimal input, but it generates a whole matrix of output. So that's called expand.grid, and the name of that would be this, expand.grid. Okay, and actually in our next, I think it's in, if it's maybe a little bit in MI210, but for sure in MI212 we have a whole lecture or two on clinical trial simulation. So there's lots to it, and generating the data set is part of it, and that can be a key part of really generating the skeleton file that you're going to simulate. Okay, so what's the second homework problem? Okay, so the second homework problem, I wanted you to do some resampling. And again, this might be where maybe you're resampling to generate bootstrap data sets. So what I mean by that is maybe you're taking a data set and you want to tweak it a little bit, as I talked about in the lecture. And in this case, I want you to generate 10 new versions of the prob1 data set, and then plot a histogram of weight for the original data and for each of the resampled data sets. And generally speaking, does the distribution of weight and the resample data sets appear similar to the original. Because especially if weight's a relevant variable, you would want to make sure that maybe that would indicate if they don't appear original, maybe you need to stratify by weight in some way. But in this case, what I was really looking to see is just writing the code to, one, do the resampling, and then two, read in maybe the files that are generated and then plot them out, plot histograms of each weight. So the first thing you have to do is you have to read in the problem 1 data set, which we have given to you. And we know what that looks like. We've seen this a lot of times, but I'll take a quick look at the head of it. So it's, again, a population PK data set. I'm going to use the resample function. And resample does something and randomly pools IDs to generate that data set. So what I'm going to do is, so that I have reproducibility here when I run it in the next step, when I ask you to do it the next time, I'm going to set the seed. So again, just a 4 or 5 digit number that sets the seed for the random number generator, so that every time I run, as long as I set the seed first, every time I run this resample step and generate these 10 files, I'll get the same 10 back every time. And that can be very important if you're, for QC purposes or for purposes of kind of being of consistency when you're running these bootstraps. And so resample, as some arguments it takes, is the data frame. So problem 1, I'm keying it on ID. As we talked about before, rekey just means that in the new data sets that you generate a new ID, because it doesn't really matter what the old ID is. You just want the new one to be contiguous, so there's a new unique one for each patient. I ask you to generate 10. So much like in MetaSubs, it takes a names argument. In this case, I'm saying generate 1 to 10, and I'm going to have it put in the modeling out.r directory. So if I go ahead and run this, happens very quickly because these data sets are very small. And remember, we're only talking, I believe, about 40 unique individuals here. Let's just take a quick look. Yeah, we only have 40 individuals in this prob1 data set. And if we move over here to the right, what we'll see is we have 1.csv. Sorry, I don't want to do that. I didn't want to click on it. But we have 10.csv, and we have 13 and 14 and 15. We have basically 1 to 10. We also have 1 to 10.csv. So we have 10 comma delimited resampled data frames. Now what I want to do is I want to plot the weights. So now what we're going to do is I'm going to write this to a file so I can show it later. So I'm going to write this to a file called prob2. And I'm just going to set some row arguments. I'm going to set basically some, for plotting, I'm just going to set, I'm going to break the page up into a 4x3 grid because I know I'm going to be plotting 11 distributions, the original plus the other 10. So the first thing I'm going to do here is I'm going to plot the original distribution, and that's simply one unique line per individual of the weight variable. And then I wrote a loop. You can do this in lots of different ways, and we'll talk about another way to do it in the next homework section. But I'm going to write it by a loop. So I'm going to loop over the numbers 1 to 10, and I'm going to read in 1 through 10.csv one at a time. Do the bang duplicated, so I only have one ID and one associated weight, and then I'm going to generate the histogram. And I'm going to also label it in such a way so that I know which resample it came from. And I'm going to do that 10 times, and I'm going to close the device. So if I run that, and I look over here in my directory, I'll see a prob2.pdf, and if we open it up, what we now see is we see the original data frame, distribution of weight, and now we see the resample distributions in each of the resample data sets. In this case, I'm not going to get too hung up on how close you want them to be. I mean, you generally want the distributions to be similar. One could argue that this distribution down here is not. We have one thing we have to realize here. We're talking about plotting histograms for 40 individuals, so we don't have a large number to begin with. So these histograms to begin with don't look very nice, and then when you start resampling them, You don't have a large number. I would argue that if you had 200 or 300 patients and you did this, these histograms would start to be look better and probably be more similar between the distributions. Now, so that's one way. The next way, and this comes into play, this idea of looking at what the distribution looks like. This can be very important, especially if you're, let's say that you are maybe your model has some relevant continuous covariate that you want to make sure the distribution of that covariate is similar, and weight here probably maybe not be so critical for this, but maybe if you're dealing with a pediatric population, you might want to make sure that the distribution of weights in the resampled data frames is at least relatively similar to the distribution you saw in the original. It doesn't have to be identical because it's not going to be because you resampled it. As the number of patients gets smaller, those distributions are going to look uglier and uglier as well, as compared to the original. Okay, so the final and third really homework problem, the fourth one we'll talk about in a second, is using the same scenario. So generate 10 new versions of the prob1 data set, but now do it in just 2 function calls. And I gave you a hint. You want to make one call to resample and one call to lapply. So we're going to take advantage of the fact that resample normally returns invisibly the resampled data sets. You normally wouldn't see them. If you're up here, what we did is we said resample, and basically normally what it would do is invisibly return. It doesn't get captured anywhere. It returns each of those resampled data sets as a list. So what we can do is we're going to set the seed again so that distributions are going to be identical this time again, the same resampled subjects. Now what we're going to do is we're going to assign the output of resample to a new R object called simWeight. Same arguments we had before. And if we take a look at simWeight, what we also noticed, what we didn't do is here where we specified an output file, we didn't specify an output file down here. So the output, there's no outputs being written to the actual computer itself. If we take a look into a structure on simWeight, what we'll see is a list of 10 objects. Each of these represents one of the resamples. So here's the data frame for resample 1, here's the one for resample 2, and there's 10 of them, and they're a list. So now that we have a list, we can take advantage of that list, and we can apply a function across each of the elements of that list. We're going to do this in kind of a, maybe I cheated a little because I really used 3 functions here, not 2, because I'm going to I wrapped sapply, I wrapped lapply around sapply, and the reason being sapply is going to give me out a vector of what I want. So for example, why don't we'll just run the interior of this first. So the inside of this function is sapply, and I'm running it against simWeight. The function I'm calling with sapply is subset, and then the arguments to subset are bang duplicated on ID, so I'm going to limit it to 1 ID per row, and what I'm going to be selecting out of that simWeight data frame. And if I just run that portion of it, what you see, what gets output to lapply is a number of, it's basically 10 vectors of weights. 10 vectors of weights that correspond to the weights from each of the resampled data frames. So what I'm going to do is I'm going to go ahead and wrap that result now in lapply, and the function I'm going to call with lapply is histogram, and I'm going to say give me histograms with at least 4 breaks, and that's the same plot that I called up here, histograms with 4 breaks. So now I'm going to write this now to prob3 instead of prob2. So if I do that, there'll be some other output to the screen that's going to come out, which is basically the results, or the statistical output, you would say, from each of the histograms that's plotted. So if I take a look at prob3 now, it's going to be hard to show you both of these, but we'll try and show some of them. What I don't have in the new output, I didn't replot the original data set. I just replotted the 10 resamples. And so resample 1 here corresponds to histogram X1XL and 2XL, then 3XL. And if you'll notice, these histograms are pretty much identical with respect to the way they look. Actually, you'll notice up here, actually, what I didn't do properly on this plot up here in the first prob 2 is I didn't actually bang duplicate it appropriately on the script. So you can tell that by the fact that there's frequency of 250 instead of a maximum frequency of, say, 20 or 30. But the short here, the main thing here is really that you can, it's just to kind of get some expertise really in using resample and MetaSub and how you might use it. And the kind of take-home message too, that when you do these resamples, especially when it comes to a variable that may very well be important covariate in your data set, you probably want to take a look at the distributions that are output on the back end from that resample to make sure they look similar between the observed and between the observed data and your resample data frames, as well as you're comfortable with what they look like. They're not ugly. Or maybe they're ugly to begin with, it doesn't matter, but you at least want to get an idea if it's something that's relevant, that they're similar between your resampled and observed data. Okay, that's the homework. The last thing, and I'll ask you to do this on your own, which is read in, output, and generate 3 to 4 diagnostic plots. Again, nobody has to share this. All I would ask is, did you encounter any problems? What kind of plots did you create? And if anybody has done this, just pop up your answer to the question block. I'll just do a little bit of, in the meantime, while you do that, I'll just tell you what I expected some people to happen. Depending upon what you've read in, the output that you read in, sometimes you may read in an output from, it depends on what kind of modeling you did or what you've used, but basically occasionally when you read something in, the attributes aren't set properly. So for example, maybe time because it had some missing variables, or maybe DV because it had something like a variable called BLQ in there or something like that in the actual row. Maybe it got read in as a character rather than a numeric, and so you had to do some conversion of that to numerics before the actual plotting worked. Oftentimes I'll find myself running into that issue where I'm reading in, say, not necessarily an output from a model, but maybe a data set, where a column may, a column like concentration may have in it things like non-numerics. It may have in there something like dots, or it may have in there something like letters like BLQ or LLOQ or less than 5, something like that for the concentration value. And when you read that in, R doesn't really know what to do with that, so it either converts it to a factor, which is not very helpful, or you could say as is equals true on the read table step or read table step, and it'll convert it to a character, and then you have to do some conversions on the back end inside of R. But if you don't, you can lead to some funny plots, some very funny looking, say, concentration versus time plots. And I think there may even be some issues when you're reading in the data sets we gave you for the project. You may run into that too, where there might be some non-numerics in what would expect to be a numeric column. So you may have to tweak that a little bit. So anyway, that's really what I was looking for. I wasn't looking for, I didn't expect, you shouldn't have lots and lots of problems reading in output at the moment, given the experience you've had with this class. Anyway, so that's all for me of talking today, at least. So I'll open this up to any questions anybody might have, either on this material or anything else we've covered this week. Yeah, actually, that's a good point. Somebody wants to know about the grid option in non-R, and actually the grid option is, let me pull up the help here, and maybe that'll pull up the help for non-R. So we have on the screen here the help for non-R, and grid is simply a true or false, and it really depends, it doesn't do anything other than if you say grid equals true, which is true for the environment you're running on, because we are using a batch processing tool called SunGrid Engine. If you say grid equals true, MetaSub knows how to deal with an interface to SunGrid Engine, so it knows to distribute that run across either one of the 8 cores that we have in the computing environment you have. So for just as a little bit of background, when you log into RStudio, what you're logging into is a system that's a multi-core machine. So there's 8 cores. It's one machine with 8 cores. And when you submit a given NONMEM run, when you say grid equals true, all that means is that the NONMEM run goes and gets run via SunGrid Engine or via some batch processing tool. What that means to you all doesn't mean a whole lot. Your run still continues and everything happens, but let's just say that all 12 of you or 20 of you were to log on at one time and submit a NONMEM run. Well, we don't want 20 runs going on an 8-core processor at once. So if that were to happen, 8 of those runs would run, and the other 12 runs would sit and pend and basically wait until one of those runs finished, and then it would be run. It's just a way of handling kind of computing in a multi-core environment. And then the question actually, that's and what you're really dealing with here, in this case, you can think of what you're running on as a small cluster. I mean, cluster, grid, whatever you want to call it, but you call it potato, I call it potato, but basically a grid, in this case, you have a grid that's got 8 cores. You could very simply, we could very simply have another machine that would exist as part of this grid and add another 8 cores to it, and now we would have 16. And because we have SunGrid Engine running, and because we're using something like MetaSub, it would then share your runs across those 16 cores. And when I say share, I'm not talking about parallelizing here. I'm not talking about splitting one run across 8 different cores. I'm just talking about taking a run that's run and shoving it off to one of those cores. So if you submit 8 or 10 runs, if you submit 8 or 10 runs, then 8 or 10 runs will run at once. And if you submit more than 16, in the case of an environment that had 16 cores, some would run and they would all run, and the other, those above 16 would pend. So yeah, so really what we wanted to do here, we don't want to get people confused with this whole idea of grid or not, and so that's why we just specify in the case when you're running here on our system, you say grid equals true. So there's another question here. Do I have an example using the grid option? Well, I can try the expand grid option. Let's just see if we can get something off the cuff here. Let's say that we want to, let's put a little comments in here. We want times to go from 0 to 24 every 1 hour. Okay? So let's say times sequence 0, 24 by 1. So now I have a variable called time. Tim really, that goes from 0 to 24. Now let's just say that I have another variable called, I don't know, ID. Let's just call it IDs. And it's going to go from a sequence of 10 to 20 by 1 again. So we have ten IDs. And let's say that we want to have a variable something like sex. And it takes 0, 1, males and females. And so now we have a variable called sex. And let's say that we want to make a skeleton data frame. And this is a very simple argument, but let's say we want to make a skeleton data set so that for each ID, they have those time variables, and for each ID, we have possibility of being sex 0 or sex 1. So we could do something like the following. Example, expand grid, time, IDs, sex. I think let's take a look at the help for expand grid here once. Okay, so what does it do? It creates a data frame from all combination of factors. So in this case, our factors are time. Oh, you know what? I used the word time instead of Tim here. I think that should do it. Let's take this out. So now, what does example have in it? We can look up here. Example has in it 550 observations of 3 variables each. Now, what I could have done to make it a little bit simpler here so I knew what I was doing, maybe we want to do something like time equals ID equals sex equals, something like that, so we know what each of these variables are. Now, if we do head example, well, we have for each ID, probably not relevant to, in this case, take on the sex of 0 and 1, but for each, so now what we have is we have a larger data frame, and we did this relatively easily, that has, for every ID, it has all the time variables, and it has all the sexes as well. So you may not want to do that, say, for males and females. You might want to do that a little bit differently, or go back in and change it in some way. But that's kind of a down and dirty example of expand grid, and that'll get you part of the way to what you need. I mean, you can do this a bit more. You can get a bit more fancy with putting in dosing and things like that. But that's kind of the nuts and bolts example of expand grid. So it just takes as an argument a number of factors or variables, and it basically creates expands those variables for every combination. So it creates the full matrix of ID, time, and sex. It's a step in the right direction when you want to generate. Start with a skeleton data frame. You have to give a little thought to where you want to go from beginning, before or after that, but that at least gets you started on using expand grid. I'll actually let that little example in the homework script that I post. Just as a brief example of expand grid. Okay, well, I'll keep it open for another few minutes, but you feel free to go or stay or ask any questions. If I don't hear any questions for a couple minutes or so, we'll just we'll close it out and let you know that. Again, just as a reminder, please make sure that you do the final exam between now and next Thursday. you can submit the answers. You can do them part of the way, but once you submit them, they're submitted. You can't go backwards once they're submitted and everything's done from the website. And also make sure that you get your projects in. They need to be in by next Friday at the latest. And the machine, the RStudio that you're connecting into, will be around through the end of the year. And then after that, it may still be up, but I'm not going to guarantee you're going to be able to access it, or that your accounts will still be there after the 31st of this year. So if there's anything that you want from your particular home directories, it would be good to use the export function here, over here, and where it says more export. You can choose a bunch of files you want to export, and it'll export them as a zip file to your local directory, or wherever you're going to. And then next week will be the last lecture, and that'll be Jim Rogers. And as you're probably aware, nothing from next week's lecture is on the exam, so you have everything you need to complete the exam, the lectures you've had so far this year. So good luck on that. And if I don't talk to anybody, have a nice holiday. Though Jim Rogers will be here next week to teach the final lecture in the MI205 class. Oh, so somebody wants to know, how do you control the output? Well, I mean, there's you can specify a page height and width, as I've done here in one of the examples. So this is actually the page of the device you're putting the plots to. So in this case, I say I want an 11 by 17 inch page. If you're using base graphics, which is where histogram comes from, you can specify how many plots you want per page. So now it's going to create basically a 4 by 3 plotting area to put plots into as it goes from upper left to lower right. That's how you might do it for plot. And I would say you have to kind of experiment with, do you want 3 plots stacked one on top of each other? Do you want 3 plots going across the page rather than vertically? Do you want them horizontally? You have to kind of experiment with what looks best for those. And then doing that for XY plot or the lattice, there's a layout feature. So you could do something like, as part of your function call, your, say, XY plot call, something like XY plot, A tilde B, whatever that is, data equals test. There's also a option called layout equals, and that takes basically rows and columns. So in this case, you get a 3 by 3 matrix of rows and columns on each page. So if you're plotting 24 plots, it would put 9 on the first, 9 on the second, and then whatever's remaining on the third page. And again, you got to play with this layout value to get them to where you want them to be. So in the case of the example somebody asked, is maybe they're too tall and thin. If you wanted to, maybe if you're using something like XY plot, row 1, 3 gives you 1 row and 3 columns, so that's going to be tall and thin. You could also do that'll be wide and fat. You could also do 3, 1, which is going to give you 3 rows and 1 column, which is your wide and thin. Or if you want to plot 3 plots, you might just say 2 by 2, which then plots 3 of them, but it gives them each 1/4 of the page, and of course the 4th place is empty, but that's okay. I mean, that's okay that you don't completely fill the page. There are more advanced ways of splitting that up, which I think Jim will talk about tomorrow, using grid, or not tomorrow, Tuesday, using grid graphics, the gridding system on top of lattice. So he'll talk a little bit about that next week in advanced plotting. I think he showed maybe some ways in the past how to do it. If it's related to the project, don't get hung up on making it pretty. Just get the plots output and make sure you get some information for us so that we can evaluate the rationale, so you can evaluate it. So I wouldn't spend a lot of time making sure it's pretty. We just want to make sure that you got the point across. So, okay, I think that's it for today then, everybody. Thanks. Jim will be back. Roger will be back for next Tuesday and Friday's class. And that'll be it for me this year. So all you have a good holiday, and thanks.